Hi everyone. So my name is Stephen Elrington, and I'm a physics graduate student at Yale. I work with Sean Barrett's lab, and our lab we do magnetic resonance on solid state samples. And today I'm going to be talking to you about some of our experiments that we've been doing recently, where we're taking our understanding of relatively simpler spin systems and applying our understanding of that more complex biological systems in NMR in order to come up with images. So before I actually start this talk, I just want to see, by a show of hands, how many of you in this room have had an MRI done before? Wow, that's kind of, I guess, roughly half of you have somehow done an MRI. So you're familiar that this is a technique that involves a big superconducting magnet, and it's a very sensitive measurement of the atomic nuclear spins that are in the case of MRI, in hydrogen. So just for a quick recap of nuclear magnetic resonance, some of you might be familiar with that, as I said, that's the nuclear measurement. And it's using the fact that we have these nuclei that have magnetic moment. So therefore, if they're subjected to a magnetic field, these nuclei which have magnetic moments, which can be approximated kind of like a bar magnet, they will tend to precess in this magnetic field. And this frequency at which they precess is going to be given by this gamma here, which is that's called the gyromagnetic ratio, which is proportional to the magnetic moment, and also to the field strength of that magnetic field that's applied. Now, in an NMR experiment, what we do is that we have a sample, a pickup coil here, which will measure the EMF that's induced by this precessing magnetic moment. And due to relaxation properties that often occur in the sample, if this precessing magnetic moment will eventually relax back to an equilibrium position where it's aligned with the field. And that time constant is given by its relaxation constant called T1. Now, the data that we collect in an NMR experiment, it's a time domain data, and the NMR signal is this induced EMF. And you can notice two things. One is that this oscillates, and another thing is that this decays with time. So in an NMR experiment, we're not just concerned with the time domain data, but we're primarily concerned with this frequency spectrum. So if this is the magnetization of this magnetic moment that's measured in our experiment, what we're going to look at, we're going to do a Fourier transform of this time domain data to get frequency information. And this frequency spectrum would be centered at that normal frequency of precession with some sort of spread, which is given by the fact that in the sample, not all spins actually see the same value for the E naught, so therefore they precess at slightly different frequencies away from resonance. So one thing that accounts for this decay is the fact that if we have in an NMR experiments all the spins that are aligned initially, after some time, because these different spins are precessing at different frequencies, because of different magnetic fields, they will tend to spread out, and thus this magnetization vector is less and less as time goes on. And this occurs at a relaxation time of what we call T2. So the thing that's most important in our NMR experiment is actually this frequency spectrum. So in order to make the leap from NMR to MRI, we need to get this frequency spectrum and encode it spatially. And the way that we do this is first by looking at an NMR experiment where if, for example, in this experiment we have a very constant magnetic field, then for our signal, we're going to see that the green pillbox and the gray pillbox, they will have spectra that overlap because both of these spins in these different containers are seeing the same field. Now the trick is, in magnetic resonance imaging, what we do is we apply a magnetic field gradient so that, for example, the green pillbox sees a slightly lower field, and thus it precesses at a lower frequency, which shows in our spectrum. And then this gray pillbox is going to see a higher field, and thus it precesses at a higher frequency omega. Now, this is the principle behind MRI, and in order to do that, you can see that first you need the spatial resolution. So you need very tight lines, for example, very narrow lines in order to resolve the distance between, let's say, this red blue box and this blue one. And in liquids, so if these two containers were filled with water and liquids, you would see a very narrow spectrum for these two. But then if you were to say, for example, look at these two buckets, like buckets of ice, then something different happens. We actually have that the lines for these two spectra are broadened. And not only that, the amplitude of the spectra will be decreased as well, because the area on the curves have to be conserved. So this is primarily what makes MRI of solids really difficult, the fact that you can't get a high signal, and also that the signals aren't spectrally separated, so therefore you can't build up an image. So now I'm just going to take a step back and look at MRI for a bit and how, I guess, like how it's used clinically today. So it's primarily a liquid measurement, and it's primarily looking at only one atomic nuclei, hydrogen, that's in water of mobile fats. So this here is the periodic table of elements that's accessible to NMR. So each of these elements represents an atomic nuclei that an NMR experiment can potentially be done on, and you can get a signal from it. However, in the clinic, this essentially is what the periodic table looks like for clinical MRI. And it's particularly for some practical considerations, namely that there's a high magnetic moment, so protons tend to have the highest magnetic moment, and also that they're the most abundant, they're really abundant, they're very abundant in the body. And also, I guess, so here, it's not quite sure as clearly, but this is an MRI that's done on my knee. And from this is, I just want to highlight that this is a liquid measurement, so it's water molecules and the mobile fats, and not necessarily the bone, even though the bone might come up brightly. That's merely due to the marrow space and water and fats in the marrow space. So from this also, you can gain different contrast because it's the same, this is the same knee, except that we're just, for this experiment, they're changing the pulse sequences, so the pattern of the radio frequency pulses that you use to excite your sample in order to get contrast. Now, the goals of my research is to use MRI to image solids directly and not an indirect measurement. And in addition to that, I want to make MRI more accessible to other nuclei, not just hydrogen. So in order to do this, we first have to consider what are the terms acting on these solids, on these spins in the solid state, and how we can overcome them. So looking at the relevant Hamiltonian, we see that if we have a collection of spins, let's say, so we have this collection of magnetic moments, there are two main terms that are acting on them. One is the Zeeman Hamiltonian term, and that's due to the local magnetic fields of bonds of electrons. And the other one is the dipolar term, which is due to the interaction between spins of the same type. Now, these two terms are primarily the reason for the broad spectral lines of solids. So we need to, so our approach in the lab has, we've used, there are a number of ways to really reduce these two terms, but our approach in the lab has been to use these series of pulse sequences in which, over a certain period of time, we're able to reverse whatever action of these Hamiltonians have on those spins. So now I'm showing you what the general, I guess, what the general scheme of the pulse sequence is. So here we are looking at a pulse sequence, and this horizontal axis is going to be the time. Now this consists of 3 different times. One is this delta period, the other one is 4 times that, 4 delta, and then we have a third bit of delta. And so in the first period, delta period, we have a signal that's been prepared for us, and we let it decay. So you can see that it's a very sharp decay, which would correspond to a very broad spectral line in the solid. Now during that first delta period, the two terms, Zeeman and the dipolar Hamiltonian terms, they act in order to cause that decay. And then after that, do nothing period, we have a period of 4 delta where we apply a series of pulses, and the effect of these pulses is to, in that time period, make the net Zeeman term be 0, and also have this dipolar term, which is negative of, which has a different sign of the previous dipolar term. So after applying these pulses, then again we wait at another time delta, and in this time actually the Zeeman term has been flipped, but the dipolar term acts in the same sign as it did before. And what happens is at the end of this period, at the end of these 6 delta period, we have that these terms canceling out each other. So our spins at the end of this 6 delta, they basically forgot what happened between. And we can see the signal, it builds back to form an echo, and we could acquire a point right here. So, so in our experiment, what we do is that we repeat this. So whatever magnetization is built up at this very last point, it's fed into the beginning of this pulse sequence again, and we do this over and over again to build up a very to build signal that lasts much longer. So this works particularly well for systems that just have one type of spin. So here is data that a previous grad student got in the lab where they're looking at silicon, and this red line here is actually the decay of an FID, so of that NMR signal without a pulse sequence. But then if we have a pulse sequence and we stroboscopically sample the heights of those echoes, then we're able to build a signal that lasts much longer. And when you look at the spectral width, it's around 70,000. It's around 70,000 times narrower. So that works well with just a single spin system, but then wondering if this can go to a more complicated biology. We went to look at phosphorus that's in bone. So knowing that that phosphorus in solid bone is sequestered in it's in a nanocrystalline form, and our group was able to use this that whole sequence as building blocks for an imaging sequence. Where here I'm showing a port rib that we imaged below using a pulse sequence, and this is just an isosurface view, so it's connecting all the points with the same amplitude of NMR signal. And doing this, we're able to obtain sub-millimeter resolution, which is a first for these type of MRI images for phosphorus in solids. So it works well with hard solids, looking at bone, and then going ahead. The previous grad student down here, Ms. Craig, she also looked at soft tissues. So here is an image of a mouse brain. It's also an isosurface view to show like the first 50% of the maximum signal. And then going in, this section here is also 70% of the maximum signal, maximum pixel. And then here, going in a little bit more, there's a structure that we tend to see, which is around 90% of the maximum signal that you get. So using this approach, we're not only able to see with good resolution, but we're able to make out anatomical detail. And however, this is just a phosphorus density image, so the contrast only comes from just the amount of the amount of phosphorus nuclei that you have in each pixel. So one caveat of this is that even though we're able to reach sub-millimeter resolution and also able to image other nuclei using our linear technique, the imaging times are very, very long. For example, for this brain, it took around 83 hours to image. Now, in addition to very long imaging times, there's a low signal-to-noise ratio because traditionally, because hydrate has a higher magnetic moment than phosphorus, it means that anything that you're imaging that's not phosphorus will have a lower signal. And this contrast, as I alluded to before, is just mainly due to density and not any other parameter. So we hypothesized that even though we've gotten very good results using this approximation of just having one type of spin in our system, we hypothesized that we can go a step further by revising this model to include the fact that in complex biological systems, there's going to be at least one of the nuclei that we have to think about. So here is where my research comes in. So instead of just looking at phosphorus nuclei, I also consider the fact that we have hydrogen nuclei that are in the sample as well, and they can't be ignored. So for bone in particular, which is, so I'm going to show you data that's just been collected for bone only and ignoring any other soft tissues going forward. So for bone only, bone mineral is primarily approximately 7% made of calcium hydroxyapatite. And for every 3 phosphorus atoms, there's 1 hydrogen in this nanocrystal. So that means that that hydrogen and phosphorus, these two spins, they can interact with each other, especially because they're not separated by large distances. And ultimately, what that means is for a spin Hamiltonian, just looking at the dipolar term, so that's the term of these nuclei that are interacting with each other, we have to add not just to the homonuclear term, we have to add this heteronuclear term, which instead of having 2 phosphorus nuclei that are interacting, we have a phosphorus interacting with the hydrogen. And the strength of this heteronuclear term, that's going to be dependent on the distance of phosphorus atom from hydrogen, as well as the relative abundance of these 2 species, in addition to orientation, because this is a dipolar term. So moving forward, the approach was to prepare signals, so to prepare your NMR signal on protons, because protons tend to have a higher magnetic moment, which means that we can potentially get higher signal from them, as well as we can perhaps get faster imaging time, because protons tend to relax a lot faster than phosphorus. In addition to having added contrast, because if we prepare a signal along hydrogen and then transfer it to phosphorus, then we'll be selecting for the phosphorus atoms that are close to hydrogens primarily. Okay? And then, so we use hydrogen when we want it, but then we ignore the hydrogen interaction when it's detrimental to us, because our whole sequence only refocuses the homonuclear dipolar terms, and it's unable to refocus any of the terms that occur from hydrogen interacting with phosphorus. So in the first part of the scheme, we're going to make hydrogen deliver its magnetization to phosphorus, and in the latter half, we're just going to lock this interaction entirely, so that we have very little, so a signal doesn't decay so fast. So this first part looks at the increase in signal part. So here, we're trying to transfer hydrogen magnetization to phosphorus using a technique called cross-polarization. And in theory, this can give us a signal enhancement of approximately 2.5, which is the ratio of the magnetic moments of hydrogen and phosphorus. Now, I want to direct your attention to this graph right here, which is showing the fact that, so this type of exchange only happens once the field that you're mutating your hydrogen nuclei around it's equivalent, the ratio of the phosphorus and the hydrogen field, B fields that are used in your experiment, if that ratio is the same as the ratio of the magnetic moments, then you're able to see this mixing of your signal. So here, this yellow represents hydrogen transferring its magnetization to phosphorus once you have this matching. But then, aside from that, you don't have transfer of magnetization to phosphorus. Now, that's all well and good, so I was able to do that, but on the right-hand side, we see that, well, it seems that the signal that we're transferring to hydrogen is much less than that to phosphorus. Than that compared to just natively excited phosphorus. And that's primarily due to the fact that they're relatively low hydrogen in abundance in bone apatite. So we're looking at different ways to try and boost this signal. But for the time being, we can probably look at the fact that hydrogen, transferring hydrogen to phosphorus is a faster process. So maybe we can win in SNR if we're able to repeat these experiments, because we don't have to wait a very long relaxation time. So here's a graph showing showing a little bit of the dynamics of this transfer. So I want to direct you to this table first. So these are listing the relaxation properties for the phosphorus as well as the hydrogen nuclei for either synthetic hydroxyapatite or dry bone. And we see that on average, yes, the hydrogen relaxation happens on a much faster scale than the phosphorus. Now, this graph on the right just shows the magnetization, it just shows the recovery. So So this graph on the right just shows a signal that you get given a certain repetition time. If you wait longer for your signal to recover, then you can get a higher signal. Even though phosphorus occurs at a very a long time, we're finding that using hydrogen to phosphorus cross-polarization, we can get a signal 5 times faster. So that just covers the part where I look at the signal. Now I'm going to look at the second half where I try to turn off the interactions between hydrogen and phosphorus. And in this graph, these are spectra that are taken using our line narrowing technique. However, in the black, we're just using our line narrowing technique. And in the red, we're turning on what's called hydrogen proton heteronuclear decoupling to basically get rid of the heteronuclear current between hydrogen and phosphorus. And here we see that we're able to decrease the line width by approximately 33%, and it's reflected by the fact that the FID lasts so much longer. So at this point, I'd like to just give the future directions. So we like to boost the signal inbound to the theoretical value and beyond. But if that doesn't work, then we can also focus on soft solid experiments, which have more hydrogen in which to take signal from. Also, we want to implement this cross-polarization technique and decoupling into an actual imaging sequence because the results that I showed were just NMR sequence results, and just build up an image and leverage the fact that we can get added contrast from that transfer. And also, we're going to look at the sparse sampling as a way to really decrease imaging times. And my lab mate, Jared Robney, is going to speak, he has a poster on some of the ideas that we have in the lab to accelerate imaging and accelerate imaging by using some very sparse sampling methods. All right, well, at this point, I'd like to acknowledge all who made this research possible. Sean Barrett, my thesis advisor, Mary Beth Fry, who's from Princeton, as well as our funding sources, and a Yale PD, which has been very instrumental in my development as a very good student. All right, thank you for your attention. At this point, I'll take your questions.
Any questions? So yeah, very nice. I was thinking how you're going to deal with the hydroxyapatite problem, and you're right. There's a few OH groups in there, and at least they would be in constant orientation, right? You said that was an issue, but then you've got a lot of hydrogen and phosphate in marrow. So if you have a high marrow density bone, you've got that as part of the signal. So I'm wondering how you're going to make this work, and what part the orientation effect is going to play, since it's probably fixed in the hydroxyapatite, but highly variable in the marrow.
Okay. All right. So I think I'm getting 2 questions from you. So one is
at least 2.
Yeah. Okay. So one is asking exactly, I guess, like if this could work at going to something that's more in vivo, like wet bone, perhaps. And
yeah, wet bone, of course, right? Isn't that where you're going?
Yes. So I hypothesize that we're going to have more hydrogen nuclides that are in the sample. So this will probably increase the efficiency of this polarization transfer from hydrogen to phosphorus. Now, to your second question about the fact that in the crystal, both hydrogen and phosphorus, they are static, so therefore that dipolar term, I said it depends on orientation. So that's one of the primary reasons why there is a rapid decay, because dipolar terms don't in solids don't average out because of molecular motions. So far.
So are they set advantageously or disadvantageously, the orientations between the phosphorus and the hydrogens?
Well, I won't be able to say like if they're set advantageously or disadvantageously, but I can say that that just thinking about not thinking about a static sample, I would think that better to have motional narrowing of, motional averaging of those dipolar terms. Because I mean, and here I'm thinking about liquids where we benefit from the fact that there is no static angle between dipoles.
So how about the Merrow contribution? As in different modes, you're going to have different Merrow fractions.
Yes, yes, and that may turn out to be a very serendipitous method of contrast. So that's something that we can look forward to. I mean, I'm excited to bring this to soft tissues actually because they're more ancient and more, more messy, but potentially a better, more fortuitous system.
I think probably better move on, so let's thank Steph again.